All right, so we got into some different topics a little bit last time. We got into, I believe it should be chapter 16. We started talking about thermodynamics. And remember that when we talk about thermodynamics, a lot of what we're looking at, especially in sort of this chapter, is the idea of whether or not a reaction will be spontaneous or not. And remember that if a reaction is spontaneous, basically what that sort of means is it will basically occur. It will happen under those conditions. Remember as well that it really doesn't have much to do with whether it is sort of a fast reaction or a slow reaction. It just really does mean that, it will sort of occur. If a reaction is non-spontaneous, then obviously the opposite is true. That reaction under those conditions would not be expected to actually occur. Remember, again, it's the kinetics that we talked about at the beginning of the semester that deals with really how fast or slow the reaction will take place. So when we look at whether or not a reaction is spontaneous or not, there's a couple of other sort of thermodynamic values that we look at in this chapter that sort of complements the first law of thermodynamics, which dealt a lot with delta H, which again is our enthalpy. And that is our heat of a reaction. And it does obviously integrate a lot with what we'll be doing in this chapter. And again, some reminders that we talked about. Obviously, as the delta H value is negative, that's going to be an exothermic reaction. Heat and energy going to be released. If the delta H is positive, it's going to be an endothermic reaction. And that means heat and energy is going to be absorbed. So as we talked about, although we may think of exothermic reactions as sort of guaranteeing that the reaction is going to be spontaneous, it's not really the thing that we could kind of use to determine whether or not a reaction is spontaneous. As we saw some examples, I think the last time, of reactions that were both exothermic and also reactions that were endothermic that also were spontaneous reactions. So although delta H does play a role sometimes, and a reaction being exothermic does sort of help in sort of a reaction being spontaneous, is not really the thing that we would look to determine whether or not a reaction is spontaneous. So one other thermodynamic property that we started talking about is delta S, which is the entropy. And the entropy is really measures the amount of disorder, is one way to look at it, that's happening. And as the amount of disorder starts to increase, what we see is the entropy will increase. And the result of that is our delta S here will actually end up being a more positive value, or a positive value. And the opposite is true. If we see the amount of disorder that goes down, which would mean that obviously the order has increased as well, the entropy would decrease. And what we would see for the delta S is a more negative value for the change in entropy. There are a couple of ways that we could sort of calculate delta S, and we talked about some different sort of delta S's. And a lot of thermodynamics deals with the idea of, as we talked about, sort of a system and really the surroundings, right? Which is pretty much everything outside of whatever you may be dealing with. And when we sort of look at it this way, we could calculate something that's known as the delta S of the universe. And that is the delta S of the system, or sometimes the reaction, plus the delta S of the surroundings. And there's actually, again, two different ways that we calculate each of those things. The delta S of the reaction or the system is taken usually the delta S of our products minus the delta S of our reactants. And you would calculate that from really table sort of values, just like you kind of do with delta H. You multiply the coefficient in the balanced equation by the values that you find in the table. You also want to make sure, obviously, you look up the values for the correct state, so you get everybody in the right state when you do that. You basically add up all the entropy values for the products, and you subtract them from all the entropy values from the reactant, and you will either get usually a positive or negative number in that case. And remember that the delta S of the reaction does not necessarily tell you if the reaction is spontaneous. What it will tell you is in that particular reaction, are you sort of increasing the disorder or decreasing the disorder? And remember, one way that you can make a pretty accurate sort of prediction in terms of what your delta S should be in terms of the sign, should it be positive or negative, is you could look at the equation. And again, in any equation where you produce more gas molecules than you started with, you have more things flying around at the end, there's more craziness, you have increased the amount of entropy or disorder that would happen. In any equation where basically you produce less gas molecules than you started with, you can think of it, you got a lot of things flying around, then you produce less things flying around. So there's a lot more order that will happen in that, and it'll be more of a negative value. To calculate the delta S of the surroundings, we take minus delta H of the reaction, we divide it by the temperature in Kelvin, and that gives us our delta S of our surroundings. This negative here is important, as we talked about last time. We will see sort of this equation again, but it's derived from sort of rearranging an equation, and it does not have the negative in it. So when you are calculating delta S of the surroundings, you need that negative. And the reason you need the negative is, as we talked about, in a exothermic reaction, all that heat and energy will be transferred to the surroundings. And in terms of the surroundings, it will basically increase the amount of disorder in the surroundings, which means we should end up with a positive value for S in that situation. And the way we get that is if it's exothermic, the reaction, the delta H will be negative, and that negative will then turn your delta S into a positive, which is what we expected to happen. The opposite would be true if it was a endothermic reaction where it's sucking out all the heat and energy from the surroundings. The result of the surroundings losing that heat and energy is everybody will sort of slow down and kind of come to a little bit more order, not moving as fast. And the result of that is our delta H would be a positive value. So that positive and the negative sign will turn the delta S for the surroundings into a negative number, which would make sense since it is decreasing the amount of disorder that is happening. Remember as well, though, that the temperature of the surroundings does play an effect, as we talked about. You know, if you have a pretty high temperature to begin with in the surroundings, the added energy from that exothermic reaction will not make that much of a difference probably in the overall entropy that you got. So when you add both of these guys together and you do get a delta S of the universe that is greater than 0 or a positive number, that would mean that the reaction as it's written is spontaneous. Obviously, the opposite would be true if you had a delta S of the universe that is a negative value, then you would have a non-spontaneous reaction. As we talked about as well, we do want to always sort of watch our units, especially when delta H and delta S get involved with each other in equations. Again, delta S is usually in joules, and delta H there is usually in kilojoules there. And so you do have that 1,000-fold factor. So it does require, in a lot of cases, for you to adjust one of the units. For example, if we were calculating our delta H of our surroundings and we left it in kilojoules, we would not want to add it probably directly to that number because that's probably in joules. So again, you would be off if you just did that without watching those units. Any questions on any of that stuff there? So I think we left off with the ammonia example, right? We did that one, if I'm not mistaken. So I think this is where we're at. So we talked about sort of the first law of thermodynamics and the second law of thermodynamics. First law is the conservation of energy. The second law of thermodynamics has to do with the amount of disorders increasing in a spontaneous reaction. The third law of thermodynamics is the entropy of a perfect crystal is pretty much 0 at absolute 0 temperature. And this is our Boltzmann equation. And clearly, if you have a perfect crystal substance, there's only one way to do that. And once again, that's going to turn this into 0 when you take the natural log of 1, which will give us an entropy value of 0. There is also entropy values as we do phase changes. So as we go from one phase to the next, we are also obviously increasing the entropy. So as we go from solid to liquid, liquid to gas, we are increasing the entropy to positive values. And as we roll back the other way, gas to liquid, liquid to solid, we're increasing the order and decreasing the disorder. So we see a more negative sign. As you probably know from Chem 50, when we do a transition between solid and liquid, or liquid back to solid, that does occur at the same temperature, right? And that, by the way, is the normal melting point or freezing point of a substance. So for example, water, that is 0 degrees Celsius. There is a certain amount of energy that's required to do nothing more than take a substance from the solid phase to the liquid phase, or the liquid phase to the solid phase. Because that occurs at the same temperature, you have both phases in equilibrium with each other. And that energy to do that is known as the delta H of fusion, or the heat of fusion. And that is the energy not to change the temperature of anything, but at the normal melting point, freezing point, take it from one phase to the next. And for something like water, it's roughly 335 joules per gram. It's a specific the heat of fusion. And that would be going from solid to liquid, which would be an endothermic process, so that would be positive. Going from liquid back to solid, it's an exothermic process. It would be minus 335 joules per gram. That's also approximately 6.02 kilojoules per mole, give or take, no matter which way you go. And that's what's happening here. And obviously here is our transition from liquid to gas, and gas back to liquid. And there is also a value that's required to do that, and that's the delta H of vaporization. And also for water, that is roughly 40.7 kilojoules per mole. And that's a positive 2260 joules per gram if you do the conversion, roughly. And that would be an endothermic process going from liquid to gas, exothermic minus 2260 joules per gram, going from gas back to liquid in sort of the condensation move in that case. As you could also see, right, it takes a lot more energy to do which transition? Takes a lot more energy to go from liquid to gas, right, than it does to go from solid to liquid. And that's because as you go from solid to liquid, right, everybody is still relatively close to each other, right? A little bit more room for movement in the liquid phase, which is why liquids are fluid. But as you go from liquid to gas, you need to completely get everybody broken apart from one another, right? So they could go into the gas phase, start flying around. So it takes a lot more energy to do that. Obviously, these values are specific for water. If you're not dealing with water, they would have different heat of fusions, heat of vaporizations. This occurs at the normal boiling point for water, which is 100 degrees Celsius. W is the microstates. We saw it earlier on. It's that Boltzmann equation. So the W is basically the number of ways you could sort of accomplish something. So if you're going to do like a perfect crystal to be perfect, ideally, right, there's kind of one way to do it, and that's what that represents. Yeah. It was on that, we looked at it on that slide, I think, where we had circles, and like we want to put all 4 circles in one box, or 2 circles in one box and 2 in the other. Other questions on that? So this is the energy required basically to change the phase of a substance, but not the temperature. By the way, a throwback, right? If we wanted to change the temperature of a substance, but not the phase, we calculate the heat by using what equation? So let's say we're at liquid water, and we want to know how much energy to take liquid water from 50 degrees Celsius to 70 degrees Celsius. What should we use to calculate that? Yeah, we should use our specific heat equation, which I think is what was just said, I hope. So Q is equal to ms delta T, which is our specific heat, that being our heat, that being our mass, right? That is our specific heat capacity. Some books use SH, some books use C, and that's our change in temperature, right? So that is the equation that we use when we want to calculate the amount of heat when we are keeping something in the same phase, but we are changing the temperature. And if you do that at constant pressure, that is also your entropy value. You should do a big experiment, Chem 50, with coffee cups, right? And throw a bunch of reactions in there with some thermometers. Actually, they give you actually tools now, not more than a thermometer, but that's how they used to do. All right, so how does it relate to entropy? So clearly, as we'll see, it does relate to entropy when we talk about sort of going from our one phase to the next. The amount of energy required to do that, being either positive or negative, depending on which way you're going, will influence, obviously, our delta S of fusion, which you could have. And that is the entropy of fusion, which would be that transition as you go one way to the next. As you go from solid to liquid, right, we should be increasing the amount of disorder. So that delta S should end up as positive value because this guy is really positive. And as you go from liquid back to solid, we're creating more order, which means our delta S should be negative, really because that guy right there is negative, is why that would end up negative going in the opposite direction. And we could also have our delta S of vaporization, which again works the same way. As we go from liquid to gas, we should expect it to become a more positive number because it's obviously increasing the disorder, and it would be more negative coming the other way because really of these values, depending on sort of which direction. Sometimes people will call that the delta S of condensation going kind of the other way as well. So we'll talk a little bit more of that later on, I think. Any questions on that? All right, so let's talk about another important thermodynamic value, and that is Gibbs free energy, and it is another letter, so that's good. So Gibbs free energy is really delta G, and it is pretty much what the name sounds like. Gibbs free energy is energy available to do something, some type of work. So as we saw earlier, if we have a spontaneous process, our delta S of the universe will be greater than 0 or positive. If we're at an equilibrium process, it will equal 0. And that's because at an equilibrium process, right, things are going forward and reverse at the same rate, right? That's why they reach equilibrium, which means, as we talked about, everybody gets locked into place, which means overall there's really no change sort of happening, right? Because it's just going back and forth at the same rate. Now, for constant temperature processes, we could calculate Gibbs free energy by using this equation here, and we'll see Gibbs free energy in about 4 or 5 different equations and 4 or 5 maybe different ways to calculate it. And I'll say it now, and I'll probably say it later as well, but probably the best advice is you should use the equation that kind of fits what's given to you, yeah? So in this particular case, if you happen to be given some type of delta H value or delta S value, this probably would be the best way to calculate your Gibbs free energy. And that is the delta G is equal to the delta H minus T delta S. Once again, that's our temperature in Kelvin. And that is our Gibbs free energy. That is our enthalpy. And that obviously is our entropy. This is an equation where you definitely need to watch units, as this guy is typically kilojoules. This guy is typically joules, so you need to do some type of conversion. Personally, I usually will convert to joules and then take it back to kilojoules at the end, but you could convert the joules into kilojoules from the delta S to start with and just leave it that way. I will say that delta G is typically given as a final answer in kilojoules. So in terms of our 3 sort of thermodynamic values in units, typically, again, delta H is kilojoules, typically delta S is joules, and typically delta G is kilojoules as well. So those are typically the units that you sort of leave your answer in if you're solving for any of those guys. That's usually what you do. So why is delta G a little bit better of a value maybe to look at when we are looking at whether or not a reaction is spontaneous? We could actually use the delta G value to help us make that determination. If we calculate the delta G value and it is less than 0, which means it is a negative number, the reaction will be spontaneous as you are heading from reactants to products. So as the reaction is written, it would be spontaneous. If you calculate delta G and it's greater than 0, which means it would be a positive value in that case, the reaction will be non-spontaneous, the way it is written. And sometimes books will talk kind of double talk, if you will, but it would be spontaneous in the reverse reaction. So what that means is obviously you would be calculating the delta G for the reaction as you're looking at it. And if you did get a positive number, that would be non-spontaneous the way it's written. But if I reverse the reaction, that means my reactants become my products become my reactants. That's going to do nothing to the number, but it will change the sign of it. So if you were to reverse that reaction, it would go from a positive delta G to a negative delta G, and that becomes spontaneous. But again, we usually do quote the value for delta G or delta H for how the reaction is written. But that's what it means, that if you reversed it, it would become spontaneous. And delta G equals 0, it will be an equilibrium sort of process. Now, another way that you could calculate delta G, which is a common way as well, and I would say this way would be a situation where, frankly, all you're given is the equation, and that's it. And basically what that means is go to a table and find the delta G values, just like we did with delta H, or you did with delta H, just like we did with delta S. You basically take products minus reactants. So these would be values that you would find in a table, and you would add up all the products. You would still, again, take the coefficient and multiply by the values that you find in there, and you would subtract it from all the delta G values of your reactants. These guys are sometimes referred to, when they look it up in a table or even in problems, as the standard free energy of formation, or delta G of F. And those are basically the values that you find in a table. The delta G naught are, again, in thermodynamics, pretty much when you see the little naught value, once again, what that means is pretty much it's a table type of value. And when we're talking about table type values, these are, again, really sort of the states of everything would be if it is that type of situation. So if it's a table value or a sort of standard value, that means if you're dealing with anything that has a pressure, the pressure should be 1 atmosphere. If you're doing anything that's basically a solution, the solution should have a molarity of 1 molar. And if you're dealing with temperature, it should be 25 degrees Celsius. If any of those things are really not those values, then you're really under sort of like non-standard conditions. And we'll see an equation later on in this chapter where that occurs, and you have to do a slightly different calculation. But typically, if you look at any sort of table values, like in a book, and you look them up, those are usually the conditions that are considered standard. 25 degrees Celsius for temperature, 1 atmosphere for pressures, and 1 molar for our concentrations. Now, delta G values in a table are very much like delta H values, which means if you have anything in a standard state, like hydrogen gas, nitrogen gas, oxygen gas, or just like a metal that's uncombined, those values would be 0. So for delta H and delta G, anything like that will have a value of 0. Remember that, though, for delta S, there are values for things like that. So things like hydrogen, nitrogen, and things in a stable sort of form, you will actually find values for. So why don't you give it a go here? What is the standard free energy change for the following reaction? Standard free energy is the delta G value. Yeah. Values there should be on the bottom, I think, what you need. And those would be obviously values that you would find in a table. Yeah. So we're going to do our delta G naught of our reaction is equal to delta G of our products minus the delta G of our reactants. Once again, if it's not provided for you, you're probably going to have to look those up in a table. Your book should have some in the back of all these thermodynamic values. So starting with our product side, we got 12 CO2s at minus, looks like 394.4 kilojoules. There you go. Then we're going to add it to 6 times our value for water here, which is negative 237.2 kilojoules. That's going to take care of all of our products. We're then going to do our reactants there. So that's going to be 2 times our benzene there of 124.5 kilojoules, and we're going to add it to 15 times the value of O2, which is not listed. It is not listed because for delta G values of these guys, it is 0. Yeah. All right. Remember, anything in a standard state will be 0 there. That's uncombined. So doing our math here, that's 12 times minus 394.4 plus 6 times minus 237.2. And then we're going to subtract that from 2 times 124.5. Looks like it's going to give us a minus 6405 kilojoules. Any questions on the calculation there? Is this reaction spontaneous? This reaction is spontaneous because our delta G naught there is negative. So makes it spontaneous. Whoops. Any questions on that calculation there? So again, if you're pretty much given just the equation like that, basically go to the table, do products minus reactants, and you'll get your delta G for that. Now, looking at the other equation here to finish up on that we were looking at with our delta G sort of reaction here. Remember here again, we do have this guy is kilojoules, this guy is joules. So there is sort of like 1,000 difference there between those two. Now, sometimes in these questions in this chapter, you may be just asked a simple question of, you know, under these conditions, would you expect this reaction to be spontaneous or non-spontaneous? They may not even give you numbers or anything like that, but they may just say, hey, this is positive and this is negative. You know, what do you think? So if we look at this situation, let's just take like the first one here where our delta S is going to be positive and our delta H will also be a positive value. That would be this box right here. So this guy is going to be positive, and this guy will be positive. That means that the back end of this equation will be negative, right? But the only way for the back end, which is the T delta S, to sort of outbeat the delta H part is we would actually need a really high temperature to do that. So at a high temperature, this guy would then make this part of the equation larger than the first number, and that would result in a negative value for delta G. So at large temperatures, we would expect delta G to end up being negative, and it would be a spontaneous reaction at that part. The opposite is true, obviously, at lower temperatures in that situation. You won't have a big enough number on the back end of that equation to overtake the front number. And that means the front number will still be positive and our delta G would be positive, and the reaction would end up being non-spontaneous. If we went to, say, this box here, that is our delta S is positive, our delta H is negative in this case. With our delta H being negative and this guy being positive, no matter what we do in this situation, delta G will always be negative, yeah, because temperature's got to be positive in this case. So in this case, at all temperatures, yeah, delta G will end up being negative and the reaction will always happen. So if you got a positive S and a negative delta H, you're going to be in good shape at any temperature. You would expect that reaction to be spontaneous. If we come down to this box here, we have a delta S that is negative and a delta H that is positive. So in this case, when our delta S back here is negative, that's going to turn the back part of that equation into a positive number. And if our delta H is positive, no matter what you do, delta G will always be positive, yeah? So if you do that at any temperature, delta G is going to be positive in this case, which means the reaction pretty much will be non-spontaneous at any temperature when you have that combination of sort of charges on those things. Last box over here, we have a delta S that is negative, and we have a delta H that is also negative. So in this case, our negative delta H and our negative delta S, the negative delta S is going to turn the back part into a positive number, which means at low temperatures, that positive guy can't beat the negative delta H. So at low temperatures here, the delta G will be negative and spontaneous. At high temperatures, you're going to run into a problem because then the back part of this equation will overtake the top number and it will be a positive value. So there's a lot of cases where you'll come across problems where, again, like I said, they really won't ask you a specific numbers or anything like that, but they'll just ask you, if this is positive, this is negative, will you expect this reaction to be spontaneous? You clearly could put some numbers in there if you wanted to, but that's the general sort of pattern that we look at. Any questions on that there? All right, I think it's a good place to lay it up here.